Okay, so today what we're going to be going over is the AOI design, basically going over truth tables to logic expressions so that you guys know how to start designing your circuits. So, truth tables to logic design, to logic expressions if you were putting labels or titles in your notebook. Okay, so what we're going to be going over is basically how to properly construct a truth table. Some of y'all already may know how to do this, and you may have already seen this in the last couple of labs that we've been doing. But I'm going to make sure you know exactly how to do it and how to do it the quick way. Then we're going to talk about what a sum of products logic expression is, and that's how you're going to write one. Then we're going to talk about a truth table, how you're going to create a truth table from the logic expression. So if someone were to have given you the logic expression, how you would go backwards instead of just going straight to the logic expression. And then we're going to look at some word problems, just so that you know how to use the word problems, because in the lab you will see some word problems. So here we go. Oh, not that way. This way. Okay. So we already talked about what a truth table was, but in case you didn't get that before, a truth table basically gives you all of the possible outputs for all the possible combination of inputs that you possibly could have. So depending on how many switches you have and how many different sensors that you might have, what your output would be depending on how they switch around. So we kind of went over this when we did the last lab for the seatbelt. You had 3 different sensors that you were talking about. There was the door, the key, and the seatbelt, right? So those were all sensors that were basically giving a specific input, and then depending on how those inputs were working, the buzzer would go off, which would be your output. All right, it's the same idea. What you do need to know about a truth table is that you're going to have 2 to the power of n number of combinations. So n being the number of inputs that you have. So in our case, we had 3 for that seatbelt. So 2 to the power of 3 is what? Try again. 8. 8. So it's 2 times 2, which is 4, times 2, which is 8. Okay? So you had 8 total combinations for it. And then what you'll also recognize in a truth table is it's all just basically counting in binary. So you're starting with 0, then you're going to 1, 2, 3, 4, all the way in binary. And I'll show you that here in a minute. And then all of your outputs are listed on the left. But that's basically a truth table. And we've seen these before. This is what a truth table looks like. So we've seen these, we've used these. But I'm basically going to go over how you're going to get a circuit from that. But the first thing you have to do is get a logic expression from it, and then we make a circuit from that. But you can see in this one we had 3 inputs, X, Y, and Z, and 1 output, F1. And so you have 3 different inputs, so 2 to the third is 8. So we have 8 different rows for all your outputs. Does that make sense? Okay. And if you look at the actual truth table, you can see that Z is changing 0, 1, 0, 1, 0, 1 all the time, right? I don't know if we went over this in class or not. But basically, for Z, it's going to change every time. 0, 0, 1, 0, 1, 0, 1, 0, 1. It always switches back and forth. Okay. For the next one over, which is your Y, that's going to be your 2's place, and that's going to switch every 2 times. So it'll be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, all the way down. And then the third place, which is your X place, that's your four's place. So basically, it's going to switch every 4 times. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, right? Keep going, and it keeps going. So that's your 4th place. The next one would be 8. So if there was a letter before that, like a W, that would have 8 places. They would be 0, 8 times, and then 1, 8 times. And it would keep going like that. And then 16 and 32, and just kind of keeps doubling every time. Has everybody kind of understood that? All right. Moving on. These are 4 different ones, or 2 input, 3 input, and 4 inputs. So you can see 2 inputs, 2 to the 2 is 4 combinations, so you only have 4 rows. 2 to the 3 has 8 combinations, 8 rows. 2 to the 4 is 16, has 16 rows. We won't get much bigger than that. In this class, I don't think we get much bigger than a 4. There may be a 5 in here, but doubtful. So I wouldn't count on it. We don't get much further than this. This is why I want you guys to be able to read and understand numbers in binary to 4 digits without having to think about it. So like if I gave you a 1010, you should know that that is 10. You could come down here and look at your truth table and know that that is your 10th spot, 10th place, but you should know it without having to think about it and calculate it. Okay? But basically, if you look at this the last setup, which is your 4 inputs, you can see that, or you'll see that it's counting down. So this first row is 0, 0, 0, 0, that's 0. The next row is 0, 0, 0, 1, that's 1. The next one is 0, 0, 1, 0, that's 2. 0, 0, 1, 1 is 3. 0, 1, 0, 0 is 4. 0, 1, 0, 1 is 5. 0, 1, 1, 0 is 6. And so on and so on and so on. So basically it's just counting down in binary. So if you know how to count binary, truth tables are not hard. They're very easy. And then your F4 is just your output, what the output is going to be with that particular combination of inputs. Does that make sense? Okay. We'll move forward. So once you have your truth table filled out, and typically they'll either give you the truth table or you'll create your truth table like we did with the seatbelt. With the seatbelt circuit, you kind of had to create your own truth table with your expected or your actual numbers. Remember, we put it in multi-sim, and then you click back and forth to figure out what your outputs were. Same idea. But basically, what you're going to do is you're going to take your truth table, and you have to create a logic expression which looks like this F5 down at the bottom right. Okay, that's your logic expression for this truth table. So the way you would do that is you're going to, I'm going to move to the next one. Oh, maybe not. Okay, what you're going to do is you're going to find anywhere where the output is a 1. And so this might be something that you write down or put in your notes on how to do this, because otherwise you might not remember. But if you look at the truth table down in the bottom left over here, you'll see that we're looking at the F5 column, and we're looking for anywhere that the F5 is a 1, because that means it's going to be turned on, right? That means the buzzer is going to be making noise, or the light's going to be turned on, whatever. So we're looking for all of the 1s. Anywhere there's a 1, you're going to take and find what they call a minterm, M-I-N-T-E-R-M, which is here. I don't know if this will work or not. Yes. Okay. So you're going to take and find your minterms. All right. So for this particular one right here, where there's a 1, you're looking at these three different numbers, or the inputs for that 1. So you have a 0, you have X is a 0, Y is a 0, and Z is a 1. Do y'all see that? Okay. So the way you will write this is if it's a 0, it becomes a naught, or an inverted variable. So in this case, 0 for X ends up giving you an X naught. 0 for Y gives you a Y naught, and 1 for Z gives you just Z. Y'all see that? So anywhere there's a 0, you get a bar over it, and anywhere there's a 1, it's just that letter. Y'all understand that? Following me so far? Okay. So if we looked at this one, you have this next one is a 1 here, so this is going to be X naught, Y, and Z. So if you look over here, X naught, Y, Z, that's our minterm for that particular one. Okay, and you're going to go through and find all of the 1s in your F column right here. You got this one, this one, this one, and this one. Okay, and you're going to find all your minterms for those 1s. Everybody following? Okay, it's not hard. It's just something you have to be able to know how to do so that you can make sure this is how we're going to make our circuits eventually. Okay, so on the next setup right here, we have X, Y naught, Z naught, and here's X, Y, Z naught. Do you see how to do it? Everybody good with that? Okay, it's not difficult. It's just something you just have to know the process. So once you have all of your minterms over here, let's see if I can erase this. Okay, so once you have all of your minterms, your expression is basically each minterm added together. So over here you have the first minterm, which is X naught, Y naught, Z naught, plus X naught, Y, Z, plus X, Y, Z, Y naught, Z naught, plus X, Y, Z naught. And that's your logic expression.
Y'all get that? So you find your min terms, you add them together. That's your logic expression. Really simple. Does anybody not understand how to go from a truth table to a logic expression? This is step one of making the circuit. Anybody? We're all good? Okay, cool. Does anybody still need to write anything down before I move on to the next page? Okay, I'll give you a second. Does anybody find this to be too difficult yet? Awesome. This is step one. There's only like 3 steps. So once you can once you can do all of them, you should be able to build any circuit anytime. All right. I'm going to erase this. Maybe. I hope this is showing up on the video. Okay. Min terms. Okay. It's a weird term. It's a weird word, but it's basically what they use. They have max terms also, but we're not going to get into that really. There's also a product of sums. This is a sum of products, or an SOP. There's also a POS, which is a product of sums. We aren't going to get into. If you decide to do this in college, they'll talk to you about product of sums and all of that. And again, this is in your Canvas. So if you're missing something, if I go too fast, you have this in Canvas. You can go to Canvas and find whatever you missed. All right, moving on. We're going to do an example really fast, just so everybody's on the same page with me, and I'll probably call on y'all. Y'all just have to give me the right min term. All right, so we're looking for min terms. Our logic express, or our output is F6. So we're going to be looking for what F6 is. So we're looking at this column, and we're trying to find all of our min terms. All right. Can anybody give me the first one? Anybody want to volunteer, or you want me to just call on people?
A naught.
Okay.
A naught, B naught, C naught, D.
A naught, B naught, C naught, D. Okay, that was for this one right here. Oh, for this one. Right? Anybody not understand how we got that? Okay, so let's look at this one right here. Someone else give me that one. Go for it, Rankin.
A naught, B naught, C, D.
Okay. A naught, B naught, C, D. Right? By the way, you point this out since I made a mistake. I want you to see where I made the mistake. It's not you, Rankin, you didn't make a mistake. I made a mistake. I'm going to erase this AB, maybe. Come on. Or am I not? All right, somebody tell me why this Promethean board stopped working on me. There we go. There we go. Okay, what I wrote was this. Okay, you cannot put one line over 2 variables like this and it be the same thing as what you're trying to explain. If you put this line and it's one single line over 2 variables, it means something completely different than if I was to write something like this. Those two are not the same thing. I just want to make sure that everybody's aware. When you make one line over 2 variables, it is completely different than if you make one variable with one line and the next variable with one line. Just want you to make sure that you see that. So you can't combine the lines together. Is it erasing? Okay. I think putting it on this is messing it up. Okay, so it was what again? A naught, B naught, C, D. Okay? So we'll go to the next one. All of these are zeros until we get to this one right here. Okay. So what is that one?
A, B naught, C, D.
A, B naught, C, D. A, B naught, C, D. Everybody good with that? Okay. We got 2 more to go. What's this one I'm on right now?
A, B, C naught, D.
A, B, C naught, D. Okay, and then C naught, D. And then we've got one more. Someone else give me that. That's the easiest one.
A, B, C, D.
A, B, C, D. Thank you. All right. So those are all our min terms. Everybody pretty good with that? Everybody get that? So the only difference is now we just write it and we add them together. F6 is equal to A naught, B naught, C naught, D plus, and I write mine like this. You're gonna see how I write them, it's weird, but it makes my life easier whenever I write them this way. So I go to the next row, A, B naught, C, D. And I go to the next one, A, B naught, C, C, D. Then A, B, C naught, D. And then A, B, C, D. Just like that. Okay. It's just the way I write them because to me I can put all my midterms in a column and I can kind of see that I've added them together and I don't miswrite my logic expression. Does that make sense? This is my answer. Right here. Okay, you can do it however you want. This is just how I do it because to me that's my brain working, that I can just kind of go down the list and put them on there. Okay, and I don't mess anything up. Everybody good? That's how simple that is. So if you're looking at that lab I just gave you, this is the same answer as what we just did. Okay? We all good? Okay. Now we're going to move on and we're going to go backwards. So now what we're going to do is we're going to go from a logic expression to a truth table. Okay? Not a whole lot of difference. The only difference is that you still have to know what your what your midterms are. Okay, in fact, I think it's easier this way. So, but what you're going to do is you're going to be given a logic expression like this, and you're going to find where that logic expression is on your truth table that you're going to draw. So basically, you'll draw this part down here, and then you'll find where each one is. So in this case, x naught, y naught, z naught is what? If the naughts are zeros and the regular variables are ones, what is x naught, y naught, z naught?
0,
0,
0, 0.
0, 0. This is a 0, 0, 0. So I go find 0, 0, 0, and I put a 1 into my f. Okay? That's all there is to it. So then I'm going to go ahead and skip over to this one over here, which is 0, 1, 1. And I go find that on my truth table. So 0, 1, 1 is right here. So I put a 1 there. All right? And then this last one right here, the xz. What's missing from that? Y. That's because we don't care what y is. That's what you call a don't care situation where we don't care what y is. Y can be a 0, can be a 1, we don't care. All we care is that x and that z are both what?
1.
1. So we find where x and z are 1, whether y is 0 or not. So we're going to come down here and we're going to find, okay, we have x is 1, z is 1, so that gets a 1. We don't really care what y is. Okay? And then there's going to be another scenario where we have it again. There's 1 and there's 1. We just don't care what y is. So both of those get 1s. Okay? So the fact that y is not represented in our midterm just means that y equals a don't care. We don't care. Does that make sense? Okay. Yeah. Oh, did you have your hand up?
Yeah.
Yeah, what's up?
So it could be either one.
It can be either one. It's actually both.
Oh.
So if you look at it, like we don't care that y is a 0 or a 1. What we care is that both x and z are 1. And so we put 1s wherever x and z are both 1s.
Thank you.
Uh-huh. Does everybody get it? Did anybody not understand this? This is going backwards. It's actually, in my opinion, I think this is easier. The hard part is that you have to make a truth table, but it's pretty simple as far as what you're doing. Everybody good? All right. I'm not even going to erase this. I'm going to leave that on there. We'll move on to the next thing. All right. So I'm going to show you how to make a truth table really fast so that there's no question on how to do it. For the first thing you're going to look at is your logic expression right here. And you got to figure out how many variables you have. So looking at this first midterm, you know you've got an A, B, C, and D. Is there anything else throughout our midterm that we would need to add? Is there an E or an F or a G or anything like that? No, so there's just those 4, A, B, C, and D. So we're going to start with A, B, C, D, my logic expression, and then I'll have my output, which is F8. All right? So
The easy way and the fast way to do this is to make sure you're counting while you're doing it, but you start with D and you just go, you start with 0 and do 1, 2, however you're planning on doing this. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, that's 16 because we have 2 to the 4. So we're going to have, because we have 4 inputs. So you'll have 2 to the 4, which is 16. So I did 16 numbers going down, going back and forth. 0, 1, 0, 1, 0, 1, 0, 1. Does that make sense? Easy? Okay, for C, I'm going to do 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. For B, 4 times. For A, 8 times. Oh. The hardest part is not being messy, which that's the hardest part for me. So there's my truth table. Doesn't take very long if you do it this way. You can sit there and write it out. This will be your 0, 1, 2, 3, and just keep writing them out. But that takes forever, in my opinion, so I don't do that. I know what my truth tables count. I know my truth table is counting, and I know it's doing it in those columns. Okay. So starting with our logic expression up here, or our minterm, we're going to put our 1 in what value? A, B naught, C naught, or A, B naught, C, D. So what is our numbers? What are we looking for? Say it again. 1, 0, 1, 1. So I'm going to find that on my chart down here. 1, 0, 1, 1, which looks like it is right here. And come over here and put a 1. Like I said, hardest part is not being messy. Okay, I'm going to jump to the next easiest one, which would be this one, which is A, B naught, C naught, D naught, which is what? I know you know the answer, you just don't want to say it. Anybody? What is A, B naught, C naught, D?
1, 0, 0.
Thank you. 1, 0, 0, 0. So that's right here. I'm going to go across and put a 1 right there. Okay. Let's do this one. What's missing from B, C naught, D? A. That's our don't care. We don't care what A is. All we care is that B is what?
1.
1. What is C?
0.
0. And what is D?
1.
1. So we're looking for anything in the A as long as it says 1, 0, 1 after it. So I'm going to come down here and I should have 1 right here. Okay, and then again, messy handwriting. 1, 0, 1 was there. Then we should have a 1, 0, 1 around here somewhere. It's right here somewhere. Okay. So then we have one more. All right. A naught, B naught. So basically, as long as there's a 0, 0 that it starts with, they're going to be 1. We don't care what C and D are. Okay, so in this case, we're looking at these columns right here. Because all of these right here, they are all 0, 0, and then something else. And we don't care what C and D are. So 1, 1, 1, 1. All right? Does everybody get that? Anything that's not a 1 ends up being a 0. So you'll fill in your zeros here. I don't know how many actual zeros I missed here because my handwriting is terrible. Somewhere in that area. And that's basically what you'll have for your answer. So there's your answer right there. This is your, these are the 4 at the top. There's the 1 with the BC, B naught, or B, C naught, D. And then you've got your 2 for value terms. Okay? Everybody get this? Pretty easy? Okay, cool. Anybody writing that down still? You good? Okay. So the last part of this is how to basically look at a word problem and figure out how to answer a word problem. Because most of the time you're going to be given a description of what you want, what they want a circuit to be doing, and then you're going to create the truth table, or you're going to create the logic expression from it.
So in this case, what you're doing is we're going to look at this example, kind of see what they did here, and then we're going to kind of move on. All right, so a large fuel tank has sensors that monitor temperature and pressure. Right there, how many sensors do we have? Two. Temperature, there's a temperature sensor, and then there's a pressure sensor. Those are two different things, temperature and pressure. Both sensors output a logic low or a 0. So low can be considered a 0 also, in case you were wondering, if they are within safety range. So as long as everything's safe, it should be giving you a 0. An alarm will sound if either sensor indicates an unsafe condition is present. Create a truth table for this logic design. So basically, what they're saying is there's two different sensors here. If either one of those sensors goes to a 1, that means it's unsafe and we're going to have a problem. What kind of gate is that? Does anybody remember? OR gate, yes. Okay, that's an OR gate because either if the temperature or the pressure sensor goes to a 1, then our alarm's going to go off. Does that make sense? All right. And that's all this is showing down here in this truth table is that basically you got your pressure sensor, you got your temperature sensor, and your alarm. If either one of these two goes to a 1, the alarm's going to go off. It's that simple. Everybody good with that? All this is doing is showing you how to do a word problem. So, this is the example. Your teacher keeps her final exams in her office for security reasons. She would like you to design an alarm system for her office. The office has a window and a door that are equipped with sensors. How many sensors? 2, right? You got a window sensor and a door sensor that are equipped with sensors that output a 1 when they are secure. So that's important. 1 equals being secure or closed. Okay? When the alarm system is turned on with a key, so there's another input. The key has to be in there. So when the alarm system is turned on with a key, the siren should sound if either window or door is unsecured. So as long as the key is present, if the window or door is unsecure, then the alarm should go off. Does that make sense? So, first thing you do is set up your truth table where we have a window and a door and a key. In this case, it might actually be easier since it doesn't work unless the key's on to make the key first over here, and then you can have your door and your window, and then this is your alarm going off. Just because if the key's not on, if the key's isn't present, nothing works anyway, right? So having that as the first input actually makes your life a little bit easier. It'll all work the same, it just makes it easier if you do it this way. Same thing goes here. We have 3 inputs, so we're going to need 8. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1. Okay. So, what we know is that if the key is not present, then the siren isn't going to work at all, right? I guess this should be a siren since they called it a siren. So we'll change it to an S instead of an alarm, but it would have made the same thing. So basically, though, these 4 right here, it's not going to work if those 4 aren't, if those 4 are zeros. Does that make sense? That means the key's not even present. So for the first 4, you can just put 0 because it's not going to work anyway. However, once the key is in, basically they're saying that if either door is not secure or open, then the alarm should go off. So in this case, they're saying the door and the window, if they're a 1, then they're secure. So if it's 1, that means it's closed. Is it going to go off if the door is closed? No, it's only going to go off if the door gets opened or the window gets opened. So it's basically if they're zeros with the key in, you're going to get a siren go off. Does that make sense? So in our case, we're going to look for if either door or window is open, we're going to have the siren go off. So in this case, this first one right here, the key is on, but the door and the window are open, so it should be going off. The next one here is 101, and the door is open, so it should be going off. This is 110, so the window's open, it should be going off. And then 111, the keys in, but all of them are secure, so it should not be going off here. Okay? And there's our truth table. Then you'd go and find your min terms and have your logic expression, and that should be the end of that. So that's the same output or the same truth table that we did right here. Same idea. Does that make sense? We all good with that? Okay, so that was the AOI logic, basically going from truth tables to logic expressions and how to work a word problem.